Welcome to the 7th lecture from chapter number 7. We are studying VLSI design. In the last lecture, we studied about the rise time and fall time delays for a CMOS NOT. Right, and we studied that rise time delay is conventionally reported as the time in which the output signal, this blue one, rises from 10% of VDD to 90% of VDD. The time in between, we call it the rise time delay. And similarly, the fall time delay is conventionally written as the time in which the output signal falls down from 90% of VDD to 10% of VDD. So this is what we studied in the last lecture, and we also derived two expressions, one for TR, the other one for TF. TR is 2.2 times tau p. We derived the expression, we derived it in our last lecture, and tau p is RP times C out, where RP is, we know that the equivalent circuit can be drawn as like this. This is the equivalent circuit during the rise time, during the time when the output signal rises from 0 to VDD, right, and this is the output. And the equivalent circuit when the output rises from, when the output falls from VDD to 0 is this. Right. So this C out, the equivalent capacitance, that includes the drain capacitance for PMOS, the drain capacitance for NMOS, and the load capacitance. We call that equivalent capacitance as C out, which studied in last lecture. So TF is 2.2 times Rn times C out, right. So this is how we compute our TR and TF for a CMOS NOT. In this lecture, we are not going to study anything new, but we will be solving an example based on the information that we obtained in the last lecture. Right, here is an example where kappa and kappa p, the process transconductance values are given for PMOS and NMOS, and threshold voltages for the two transistors, the NMOS and PMOS transistors, are also given. They are a bit different from each other. They aren't the same. They are not exactly the same. VDD is given to be 3.3 volts, and C out, that includes the NMOS capacitance, the drain capacitance for NMOS, the drain capacitance of PMOS, and that of the load that this inverter is driving at its output. If we add everything, it becomes C out, and it is given to be 150 femto, and femto is 10 to the minus 15. We already know that. And two other pieces of information, they are also given: aspect ratio of N and aspect ratio of P. They are also given to be 6 and 8. This means this is not this is very close to, or maybe it can be exactly equal to the symmetric knot, because we studied that for a symmetrical knot, aspect ratio of PA should be 2 to 3 times larger. Should be 2 to 3 times larger than aspect ratio of N. It's not symmetric, but it can be close to that, because it's not 2 to 3 times higher. Aspect ratio of P isn't 2 to 3 times higher than aspect ratio of N. So it is not exactly the symmetrical knot, but can be closer to that. Right. So we are supposed to find TR, the rise time delay, and the fall time delay given this whole bunch of information. Right. TR, we know TR is 2.2 times tau p, where the time constant p, tau p, is Rp times C out. Rp is conventionally written as 1 over beta p times VDD minus. It's a good approximation for Rp. where we know that beta P can be written as kappa P times aspect ratio of P. So let's see whether all this information is given. Yes, it is given. 62 micro RP can be computed straight away because we are giving kappa P 62 micro. 62 micro, don't forget this micro, 10 to the minus 6. Aspect ratio of P is 8 and VDD minus 3.3 minus VTP 0.85. So this gives us RP some hundreds ohms, 823 ohms. So it gives us RP 823 ohms. And now we are ready to compute TR because we know we are given C out. C out is 150 femto. So now we can straight away compute TR 2.2 times 823 times C out 150 femto. Don't forget this minus 15. It's important. Right. So it becomes 272 picoseconds. It comes out to be 272 picoseconds TR. Good. Right. Similarly, we can find TF, the fall time delay. That's simple. We know TF is part B. We are going to find TF is 2.2 RN, C out. Rn is 1 over kappa n, aspect ratio of n, Vt n. Right, so kappa n is 150, kappa aspect ratio of n is 6, and Vtn is 0.7. So Rp, it's not Rp, it's Rn. Rn comes out to P 427 ohms. Rn 427 ohms. And we can find out TF 2.2 times 427 times 150. C out is the same because it's actually the lump sum, though. The equivalent TF. It is the equivalent capacitance at the output. So TF comes out to be 141 picoseconds. 141 picoseconds. So actually we have one more part to solve. C part is F max. This is the max signal frequency that we apply, and the output has definite rise and fall, and the output has definite logic 0 and logic 1. This is like if we have an input like this, the output has some delay and it is drawn like this. Right. If we increase the signal frequency at the input, maybe for example, if we do it like this, if the input signal is of a very high frequency, the output may be just able to reach its levels for logic 0 and logic 1. But if we apply a signal, that is of a larger frequency than that, we don't have definite levels at the input and the output. So if the output is rising and it reaches here, and the input level changes, so it starts decreasing, but it has yet not reached to logic 0 and the output level, and the input level changes. So the output keeps on swinging somewhere in the middle of VDD and 0. So that is a frequency. This means that Fin for this, Fin is larger than F max. Here Fin is just equal to F max. Here Fn is smaller than F max. Right, so F max is the frequency for which the output just reaches to its level before the input changes its logic level. Right, so we are going to find out the value F max. F max can be computed. F max is computed using this formula. F max is simply 1 over dr plus df. So part C can be solved like 1 over tr was 272 pico plus tf is 141 pico. Maybe tr is 272, 141. So it comes out to be 2.42 gigahertz. So 2.42 gigahertz, if we work on signals, input signals that have frequencies less than 2.42 gigahertz, we will have definite output levels at the output of the gate. If we work with frequencies that are greater than 2.42 gigahertz, we will have a situation like this where the output doesn't have definite levels because the output has yet not reached to its level and the input has changed its level from logic 0 to 1 or vice versa. So this is all for this lecture. In the upcoming lectures, we'll keep on studying more about the transient response of CMOS circuits. Thank you.